first thing is your aim of the experiment, right, and then the methodology and data taking. So, you observe the points and the experimental setup, and third part is your analysis. So, that is the basic fundamentals of any experiment, and that is true for these big experiments also. Okay. So, here we will try to discuss what are the aims, what are the goals we are looking for, we are after, and then what kind of methodology or detector system we are using, and then we will also see how we are close to probing or achieving our goal or aim. Okay. So, there is something called quark gluon plasma, right, and how many states of matter we know? Solid, liquid, gas, plasma, right. There are 4 states we know in general physics, but then there is a state called quark gluon plasma, and this is a state which is very important because this state first of all is, you cannot see it in this world in general. For example, plasma states also, it is difficult to find a state with plasma states, right, plasma states of matter. Solid, you can see so many things around you, gas also, liquid also, but plasma states is not so frequently available in the day to day life. And quark gluon plasma, this state of matter is still even more rather difficult to find in the day to day life. So, if you look at this, if you go to the inside of a matter, then it is made up of atoms, right, and then if you go inside the atom, then you have a nucleus and electrons revolving around it. What is there inside nucleus? Proton and neutron. So, long back protons and neutrons are supposed to be the elementary particles, right, but later on with scientific development and technological development, we knew that proton and neutron. For example, can you tell me why, from where, which experiment we knew that there is an existence of nucleus? Rutherford, very good. So, Rutherford experiment told us that there is a nucleus there, and these protons and neutrons were supposed to be the elementary particle in the long back time, but now we know that these protons and neutrons are made up of quarks. So, there are quarks inside protons and neutrons, and quarks are bound together with the help of intermediate particles called gluon, right. So, quarks and gluons are there inside protons, and these quarks and gluons are the, as of now, are the fundamental building blocks of matter, but these quarks and gluons are confined inside a hadron. You cannot have free quarks available. For example, electrons, you can have an electron, protons you can have a proton, but quarks and gluons, they are not freely available. And why? Because of the nature of the force, they are governed by a strong interaction, right, and in the strong interactions, unlike your electromagnetic force, if you try to increase the distance between these two partons which are bound together, then force increases. Okay. So, as far as you are trying to separate them out, you need more and more force. Okay. Eventually, you need infinite amount of energy or force to separate them totally out. Okay. So, in principle, you cannot separate them out. So, now these quarks are gluons. However, if you can arrange something or make some arrangement or make some experiment, perform some experiment such that if you make them free, so a state of matter, okay, where your quarks and gluons are deconfined from hadrons. So, quarks and gluons are confined, hadrons, you know what are hadrons. So, quarks and leptons, they are the building blocks, okay, and then from quark you get mesons and baryons. Okay. Mesons are made up of 2 quarks, for example, pion. Baryons are made up of 3 quarks, for example, proton, neutron, right, mesons are baryons. So, these mesons are baryons together known as hadrons. Okay. So, all particles which are made up of quarks are basically hadrons. So, quarks are confined within the hadrons, but if you can create a state of matter in which quarks and gluons are deconfined from the hadrons, and of course there should be in thermal equilibrium, then that state of matter is known as QGP, quark gluon plasma. So this is a state of matter where quarks and gluons are freely moving in a volume larger than nucleonic volume, because inside the nucleons they are anywhere there, right? Sorry, nucleonic volume, no? Inside larger than the hadronic volume, right? Inside the hadron they are anywhere there, but in this state of matter they are freely moving in a volume larger than the hadronic volume. So that is called quark gluon plasma. Now why this is important to understand quark gluon plasma? So let us look at this picture, the evolution of universe. I will not go into the detail of the entire evolution, but we are here today. This is the modern universe. The life of modern universe is about 14 billion years from the Big Bang. So after the Big Bang, where everything started at a point with lot of energy, universe expanded, okay, and cooled down, and the temperature here you can see here the scale of temperature. Here the temperature is huge, and then slowly it cooled down, and it is the modern universe where we are here today. The temperature went down and universe also expanded, and after the Big Bang, these are all hypothetical. We don't have any experimental evidence as such about the Big Bang, right? This state is also inflation, is basically we don't have any experimental evidence yet. Okay. There is a state called quark soup. So this state is basically quarks and gluons in some volume. So no matter is there during this time, so there was nothing, only energy was converted in a state of matter where you have quarks and gluons. Okay. So temperature यहाँ कम नहीं है, temperature is 10 to the power 23, 27 is gradually decreasing, because as expansion is there, temperature will decrease anyway, right? It's 32. Yeah, expansion and cooling. So basically expansion and cooling, and that because of that. So in true sense, so now if you go from this, so this is your state where no particles that we see were there, only quarks and gluons. They interacted in some way or other, and they form the other particles like proton, neutron, then nucleosynthesis happened, nucleus was formed, then atoms came into existence, after that molecule, and then matter was formed. And we reached to this state. Now this is a state of quarks and gluons, and since everything starts from there, because there was nothing before quarks and gluons, only the energy was there. The matter began into existence as quarks and gluons. So if you really want to understand it, so how the universe was created or how the matter was created, then best way is to go back in time and look at this state, right? So how they interact, what are the possible interactions, and how two quarks come together to form hadron, subsequently to atom, molecules and matter, right? So the interesting part of this study brings us here at the beginning of universe. So that's why people always say that we are trying to understand the creation of universe. Okay, we cannot go back in time, so what we can do? Is there any possibility to have this system? This was already there in the beginning. We cannot create another Big Bang and get this thing happen, right? So is there any possibility? So if you think in a scientific way, then you can always think of going in this direction back. You cannot go back in time, but you can go back in temperature, right? You can increase the temperature of the matter, you can compress the matter. So, if you increase the temperature of the matter such that you reach this temperature, then probably you will get that state of matter, right? Because time you cannot go back, but temperature you can go back because you can increase the temperature. So, whether this is just, you can think of doing like this. So, can we study matter at the early stage of the universe? So, how much temperature is required there? So, it is like 200 MeV in terms of MeV, which is equivalent to 10 to the power 12 Kelvin hotter than the core of the sun. Core of the sun is 10 to the power 7. So, if you can manage to do that, then you should be able to study the state of matter, which is known as quark-gluon plasma. So, this is how it can be done. You have a let us say nucleus, and there are hadrons inside the nucleus, protons and neutrons. You heat the nucleus and you will get a system which is quark-gluon plasma. So, these are quarks and gluons. So, this is shown in this picture, and here how you can do that. So, there is one possibility, there is one way we can do that. People thought maybe 30, 40, 50 years ago that if you collide two heavy ions means nucleus of, let us say, lead element, which is heavy, right. So, if you collide the nucleus of two heavy elements, then with very high speed, close to the velocity of light, then the huge energy will be dumped in the collision region and you can get that temperature. So, this is done in heavy ion collisions. So, then what do you need for this? How can we do the collision? Okay. So, how can you accelerate the velocity of a particle? You have all read about, or you can guess. Suppose you have a charge. So, ions means nucleus is charged, right, positively charged ion. So, you want to increase the velocity of nucleus. How can you do that? By applying magnetic force or electric force? Electric force, right. By applying electric force you can accelerate it, right. So, in that sense this technology of accelerators and cyclotrons came into picture. They try to accelerate the beam of particles or ions or charged particle. Okay. So, here there is a facility called relativistic heavy ion collider RHIC. This is at Brookhaven National Lab, USA, America. So, here you have some ion source, you create the ion. How you can create the ion? Because what is available to you is the matter, right. So, you can take lead plate or gold plate or gold, a small piece of gold, then you have to, what you need, the nucleus of that. So, you heat it, it will vaporize, it will become gas, and then you take some part of the gas, and if you strip out the electrons, because by applying positive charge you can positive potential you can strip out the electrons, right. So, you can strip out the electrons, and then whatever left is basically ions, and then you can push that ion into the machine and accelerate them to very high speed. That is what is done here, and that is done in stages. So, this is the big collider. So, you have, this is called relativistic heavy ion collider, and here there are two rings and these ions are moving in two rings, and there are intersection where they collide. Okay. So, this is the root S, the total collision energy 500 GeV for Pp. I will come to this, what is this GeV means, and 200 GeV for gold. This was available at relativistic heavy ion collider at Brookhaven National Lab, USA. So, then we have bigger such facility. So, this is called LHC, Large Hadron Collider. So, as you can see here, this is even larger than the RHIC. This perimeter is, or circumference is of 27 kilometer, and this is built in Switzerland and France. So, if you join our group, then probably at some point of time you will visit CERN, and you can go and see that this part is Swiss and that part is France. So, is somewhere here there is, where is Alice? This is in France, and this part is in Switzerland. So the border is somewhere here, okay, and this huge ring is not on the surface, this is inside underground, and underground is around 100 to 150 meters underground, okay. And there are four major experiments in this. So ALICE, ATLAS, LSCB and CMS, and this is the experiment where we are involved, our group is involved in this ALICE experiment, okay. So let me show this video. So this is just this video is showing you how the particles are accelerated and then you get the collision. So let me hold it here. So these are accelerated in steps. So you have some booster here, then there is proton synchrotron. So the energy is gradually increasing. If you look at the numbers, then you will see the energy is gradually increasing, right. So let me run it for you. So after that it goes to LHC ring, okay, and this is the tunnel. So this is a huge tunnel inside underground. This is the LHC tunnel, and here you see this is the beam pipe. So beam pipe is inside, and inside the beam pipe you have this proton beams moving around, and then in the interaction point you see from both sides beams are coming and they are colliding in the interaction point, and after the collision energy is dumped and that energy is converted into matter, lot of particles are produced, okay, and then you need a system to detect all these particles, okay. So let us try to understand the energy involved in this. So at LHC the total energy of collision is 13 TeV, that will go to 14 TeV maybe in next year, next year. So what is this 13 TeV? You know that electron volt you are aware of, right? So this is 1 electron volt is equivalent to 1.6 into 10 to the power minus 19 joule, right? And then these are, I kept this, I thought school students will be there, but keV, meV, GeV, TeV is 10 to the power 3eV, TeV means 10 to the power 12 electron volt, right. So 13 TeV, if you convert that into joule, then how much energy is 20 into 10 to the power minus 7 joule, very small energy, right. So this big accelerator, the Large Hadron Collider, the highest energy available at Large Hadron Collider is only 20 into 10 to the power minus 7 joule, and 1 joule is basically this much. You can, in macroscopic world, 1 kg weight object is weighing object is falling down from 1 meter, it will hit the ground with 1 joule. So compared to the macroscopic world, this the world most powerful accelerator, millions and millions of dollars invested in that, and the total energy is only this much, is small. And with this energy what we are trying to do? We are trying to reach a temperature which is at the beginning of the universe, right?
I think that must be 10.
That must be?
10 mGs, so 1 into 10.
Which one?
Ye 1 joule.
Okay, right.
1 joule need 10 joule.
Oh sorry, it's 10 joule, right, 9.8, okay, right, so it's 9.8, okay. So with this energy we are trying to create quark gluon plasma. So is it possible? Or there is a trick here, there is something which we are missing.
Come particles. Come particles quickly energy.
Come particles. I think you are going in right direction, but exact answer? Are we missing something? because with this small energy we are trying to create quark gluon plasma. As I already said, you need lot of temperature to be or energy to be there, right?
This is the energy for one particle. If you increase the number of particles, then
No, but collision happens between two particles only, and this is the collision energy, not one particle energy. This is when two proton collide, this much energy is involved.
This much energy corresponds to how much temperature?
So, no, so let us think of this way. So, when you clap, there is some energy involved, right? And you are okay with that energy, it does not harm you, right? But if you clap with a pin on your hand, same energy will be involved, but then this will harm you, right? You are not okay with that energy, with the same energy. So, in our case, we are more interested in energy density. So, this energy is liberated in a very, very limited phase space, right? And if you dump this small energy in a very limited phase space, then it can create quark gluon plasma, and that is of the order of Fermi, 10 to the power minus 15 meter. This energy is kept in a very small volume, you can think like that. So, for a very small volume, this is a huge amount of energy, okay. So, the energy density is quite large. So, in that sense we create QGP. So, and if you look at the total beam energy, so as I said, this LHC has two rings, right, because you need beams from both sides for collision. This and for that you need two beams, and these two beams are moving in opposite direction, and there are interaction points where they cross and they collide. So, one beam, if you consider one beam, so this is 27 kilometer, this circumference 27 kilometer, in that you have around 3000 bunches. So, you inject the proton not in a continuous way, but in bunches, and each bunch contains 10 to the power 11 protons, and each proton, so the highest top energy of LHC is 14 TeV, that is yet to come, but if you consider 14 TeV means 7 TeV this side and 7 TeV this side, okay. So, 7 TeV, each proton has 7 TeV of energy, and if you calculate the total beam energy, then it comes out to be around 350 megajoule, okay. So, 350 megajoule is roughly of the order of this energy. So, 400 tons train moving at 350 kilometer per hour. So, the kinetic energy involved is of the order of 350 megajoule, and if you dump all this energy, then it can melt around 500 kg of copper. So, that is why when you perform this experiment, then because you have something moving of that energy scale and things goes, let us say things goes bad, beams become uncontrollable, then what will happen? Then it can go anywhere and it will destroy many things, right? If all energy is dumped in one block of copper, then it can melt 500 kg copper. So, and sometimes what happens, beams become little bit unstable, then beam is dumped, okay. Dumping means you remove the beam from the beam line, and for that there are lot of setup there built at underground that are made up of granite and things like that. So, lot of huge tons and tons of granites are there, and whenever you want to kick the beam out because of some reason, then you dump the entire beam into that thing. And that is why in CERN, if you go and perform the experiment, then there is a notice will come that beam will be dumped at 4 o'clock. So, all the detectors and all the equipment should be in safe mode. So, then you switch off all the devices, because during the dumping it can be uncontrollable, right, and then some particles might go through your system also, and if it is active, then it may harmful. So, during the beam dump we close all the systems. So, this is how the collision happens. So, now what we actually so far we discussed. So, we need to have a temperature at very high value. For that we have the experimental setup, facilities are there which can collide two heavy ions, and we can get that energy. And in these collisions, our main aim is to probe QGP, that is the aim of the experiment. Okay. Now, what are the setups? So, one thing we need is the collider that we have. Let us keep that out from our experiment because we already have that. Now, in the collision what happens? The two nuclei collides and huge energy is dumped in a small volume, and a system called quark-gluon plasma is created for a very short time. Okay. And then from that lot of particles are eventually created. So, you left with lot of particles, that is it. You have no, because this happens in a very small time. So, of the order of 10 to the power minus 23 second. So, you cannot even think of something in that small time. So, in that small time lot of particles are created, and then from that information you have to understand the system, which is little bit not so straightforward, right. So, here large number of particles are produced in heavy ion collisions. Okay. So, the particle rate is also very high. I will come to the rate next slide. So, and there are various kinds of particles. You have pions, electrons, positrons, protons, neutrons, photons, muons and what not. Whatever particle are there available in the universe, most of the particles are created. Okay. Antiparticles are created also. Antiproton, anti-lambda, all these particles are also created. And then they have different charge states. Some particles may be positive, negative, neutral. They have different masses. Some particles will be low mass, high mass, intermediate masses. They have different energies as well. Some particles will be less energetic, some particles will be very high energetic. And they are produced in all directions, all possible directions. So, suppose interactions happens at the center, then they are produced in all around the centers. Okay. And these are the only source of information you have. So, as an experimentalist, we try to detect all particles as far as it is possible. Okay. It is, of course, it is not possible to detect the 100%, but we try to have most of the particles. And for that, a well designed intelligent detection system is required, because you see you have a lot of challenges here. Okay. So, and this is the main activity which we are involved at, building the detector. Like in our lab also, high energy physics lab, we build detectors. And when we say we are building detector, then this is the reason why we are building the detector. And then one detector cannot perform all the measurement, right. So, you need lot of detectors are required. So, then you try to focus on some, let us say I want to measure photons within this energy range, then I will build some detector. Somebody will come and he will say, okay, I want to measure muons. So, he will build another, use another technique to build other detector, and things like that happen. So, now experiments are designed including a group of sub-detectors. One detector cannot do, so you need lot of detectors. For example, let us see here, you want to measure photons, then photons are neutral particles, they will not give any signal on the tracking chambers. So, you need electromagnetic calorimeter. For electron positrons, they will give signal here, but for the measurement of their energy you need electromagnetic calorimeter. For muons, you need muon detector. For neutrons, they are neutral particle, you need hadron calorimeter, and things like that. And these detection techniques exploit the properties of particle interactions with the matter, because if you want to detect something, even you see something, that is eye is also a detector, right. Then can you see something in dark? No, because there also some interaction is required, right. You need light, and from light that falls on the object and that it comes to your eye, and then only you can detect it. So, some interaction with the matter is required for any kind of detection. Suppose you want to detect photon, then if this photon goes uninteracted, then you cannot detect it. So you need some interaction. So that is the basic things that is exploited, and that is what we study. Suppose you want to build a detector for detecting muons, then you have to understand the muon interactions with the matter, and then you have to find some intelligent technique to detect muons or any other particles. And then all these things are done inside the magnetic field. So magnetic field is used for momentum determination. You can guess what will happen when a charged particle will move in magnetic field. If you keep a moving charged particle, this question must be asked during your MSc interview. I don't know whether any one of you encountered this question. What will happen to a charged particle, moving charged particle, if you put it inside a magnetic field?
V cross B will happen.
Yeah, it will bend, right? It will change the trajectory, it will bend. And if the particle's velocity is large, then bending is less. If it is slow, then bending is more. So with the bending radius or bending curvature, you actually get the momentum information. Okay. So magnetic fields are therefore used in these experiments, and this is one of the experiments, such experiment or detector system. So this is ALICE, a large ion collider experiment. Okay, and this is one system which is made up of, the goal is to detect all possible particles produced in the collisions, right? So you need lot of systems, as I mentioned, for electrons, for protons, for photons, for neutral particle, for charged particle. So many systems are built together. A large ion collider experiment. Okay. So this system, this red one is magnet, right? This is the magnet that creates the magnetic field, and everything is inside the magnetic field. Okay. So the collision point is somewhere here, and all the systems are just about the collision point, because particles will be produced at the collision points and then they are flying apart from the collision point. And there are so many detectors, around 18-19 detectors are together, right? And they are complementary, all detectors. They all together make one detection system, and that is called ALICE. Okay. And you might have not noticed, there are two Indian flags here. There is one detector, 16 number, 16 is PMD. So I will discuss about this. This is photon multiplicity detector, and this is built in India, is fully indigenous detector. And with this PMD only, we, at least our group, get involved in these kind of mega science experiments, okay, international collaboration. So Dr. Y.P. Bhyogi, who was the speaker of the first lecture, first session, he was the man behind this PMD, and through this PMD we get involved in these big experiments. And then there is something here, 12 number, which is muon tracker. Okay, yes, muon tracker. This is built at SINP. This is mostly built at VCC in collaboration with many other institutes. If you find time, then you can visit VCC, and there is a lab called PMD Lab. You can go and see there. There are other activities nowadays, but you can find something related to PMD also. Then let us look at the vastness of this big setup. Okay, this is 26 meter long, 16 meter high and 16 meter wide. So Hawa Mahal is 15 meter high, right? And the total weight of this entire setup is 10,000 tons. Eiffel Tower 7,300 tons. Okay. So now you can imagine, this is a system which is taller than Hawa Mahal, this is a system which is heavier than Eiffel Tower, and it is installed not on the surface, it is installed where? Inside the ground. So you can think of how challenging it is. But this is very, very challenging, but don't think that this is done and all together brought to underground. This is done in parts, and you will slowly see that although this is very challenging and very cumbersome, but if you look into part by part, then you will realize that this is doable also. Okay, and this is more not that complicated as it looks as a whole, but if you look into parts, then it will simple also. So now as I mentioned, there are so many detectors, 15, 20, 18 detectors. Okay, so the basic philosophy of all the detectors are same. Okay, so what we will try to go through this photon detection technique, story of one detector, that is PMD, and that story will give you a glimpse of how the detectors are built. Okay, all detectors follow the similar kind of methodology, similar kind of philosophy. Okay, so now as I said, the object you want to detect, you need some interactions of that object with the matter, otherwise you cannot detect it, right? For photons are neutral particle, so if you have a gas detector, then it will not ionize the gas while passing through it, so you cannot directly detect the photon. So then you need something else, but you need something. So now what we do, this photon, you put a converter here, this could be lead plate. Okay, so while passing through this converter, this photon will produce showers. I don't know, you have already read, but otherwise you will read. This is called pair production. Okay, this photon will generate one pair of electron positron, and then those electron positron will radiate photons, and those photons will another pair production will happen, and you will get a shower of particles, which are basically electron, positrons and photons. And then these shower particles, because they are charged, right, electrons and positrons, if you put a detector like this, granular detector, and then they will give signals and you will get some hits. When a photon will pass through this lead converter, these showers will be produced, and then they will give signals in many segments of your detector, and then in this way you can detect a photon. And these are some other details, like you have to optimize the converter thickness. So this is basically the designing of a detector, right? So you have to optimize this depending on how many photons are expected to fall on your detector and things like that. So basically that is designing of your detector. You have to optimize the converter thickness, and there are so many things involved. And this is how the PMD, at least this is the size of the PMD. This is the photon multiplicity detector installed in ALICE experiment. So you see, this is a beam pipe. Okay, so you put all the detector about the beam pipe. Okay, because collision point is somewhere there and all the particles are flying towards you, so you want to put some detector. So you see the size, 1.75 meter high and 1.5 meter. So this is big, around 6 feet around roughly. Okay, if you open up the cover, then it looks like this. So these are all the cables for reading the signals. If you further remove the cable, then it looks like this. Okay, so you don't build the entire thing as a whole object, but you make module wise, right, for the ease in building it. So this is one module, and this is 49 centimeter and 21 centimeter. This is one PMD module. And have you been to this CERN exhibition? No. If you go there, then you will see that there is this module is already there, placed there. Okay, so this is one module, and you have so many such modules. And let us look at inside the module, because this is a module which is already covered, right? So you cannot see much of the things here. But how this module is built, let us look at this. So the size of one detector, so inside a module there are so many detectors or unit detectors. The size is of this order. This is 5 millimeter, so this is half a centimeter, 5 millimeter wide, this diameter, and 5 millimeter thick. So this is a copper, and this is made up of copper. So you can think of a cylinder of copper, so many cylinders, but not exact cylinder. This is honeycomb structure, hexagonal cell, this structure. So that kind of, so many cylinders are there, okay, and then the thickness is half centimeter and this diameter is half centimeter, and 49 centimeter by 21 centimeter, there are around 4600 such cells. This is one module. So particles can be detected with a resolution of how much? The size is half centimeter. With that resolution you can detect the particles here, right? And this size, this is kind of optimized depending on what is the particle rate, how many particles are expected to fall on this. You can have bigger also. If only 2 particles are expected in this size, then you should not have done this like this granular, okay. So, but there are so many particles expected, so you build like this, and then you can put PCBs from top and bottom side, and then you can put wires, because you know the proportional counter, right? You have a cylinder, you have a wire at the center where the cathode and anode, you apply the voltage difference, and this is filled with gas. So this is same thing. So you put PCBs from top and bottom, you insert wire, and then you get this kind of module ready, and these are the connectors for putting the electronics. Electronics are required to record the signal, okay. No, PCBs are printed circuit board, like you must have seen PCBs. And then you put some more stuff, and then everything was put inside a box kind of thing, which is side is made up of stainless steel, and there is a mechanism for gas flow, because all cells should be filled with some gas, right? Because gas will be ionized by a charged particle passing through it. And then this is the kind of final module, final PMD. It consists of 1, 2, 3, 6 module this side, 6 module this side, and together 24 modules, okay. And there are 2 such planes. So now let us look at the pictures of, once you build the module, now this building part, my PhD was almost in this building of this detector. When I joined my PhD, then this detector was building up and I contributed to this. And then one module you build it, you test it, and then if the performance is not right, then do some corrections and things like that went on, and then you install. This is at CERN. Then all modules were transported to CERN, and then there is a support structure, and you are basically installing modules. So these are different stages. So you put these green things are basically electronics things. You put on your detectors with electronics, and then of course this is a photographs. And then you put on other things, like you have to apply high voltage to the detector, right? Because proportional counter, you have a cathode and anode, and you put high voltage, right, in between them. So voltage basically. So high voltage because it is of the order of 1300 volt, okay. So high voltage, low voltage cables, and then you put electronics, because from each cell you need a signal, and that has to be collected. So electronics is required to record the signal.
Why do we need high voltage? High voltage?
Oh, so the voltage, why that high voltage is required? So what happens when a charged particle, so let's say a charged particle passes through the gas volume, it will ionize, right? In the ionization, what will happen? Gas molecules, from the gas molecule, some of the electrons will be knocked out, right? So you left with ions and electrons, and then depending on the voltage difference, these ions and electrons will move towards cathode and electrode respectively, okay. So now if your voltage is large, then what will happen? This moving electron can knock out more ions, right? Because if suppose 2 electrons are knocked out, can you get a proper signal? No, the signal strength will be very small. So you want the sufficient signal. For that you want the avalanche to happen. So a lot of electrons should be generated, and for that 2 things are required. If you put air inside that volume, then you will have different results, okay. probably the signal will not be noticeable. So that's why you need a proper gas selection and proper high voltage such that your signal is sufficient enough above the noise so that you can record it. Okay. And then you put so many cables for readout and high voltage, low voltage cables, and then you cover it. Okay. And once you do that, this is the whole structure, right? This is in two parts. So this is one half, this is another half. Then you have to, this is how it is done, right? So for PMD, because this is not that big, this is 1.75 meter and 1 meter. So if you, this was 1.5 meter, right? So if you put in two half, then this is not that big compared to other detectors. So we build it outside, all modules were integrated, and now we are transporting it. So you can see this big lorry. So it's transporting it to the, and this is a group picture here, and then after that transferring, it has to lower down to 150 meter below the surface, right? So this is being done here. You can see this is going down, okay.
Transportation is from India to there, or you have built it there itself?
No, we transferred the module to there, and then we installed everything there. The integration was done there, just above the this point 2, above the experimental hall. Underground was the experimental setup, and on the top we were installing, integrating everything. And then things were transferred, and this was just maybe 200 meter transfer by this lorry. And why this big lorry is? Because if you transfer it using some other mechanism, then there may be a lot of vibrations, right? So, and that might not good for your detector, because inside this each cell, as I shown there 4600 cells, inside at the center each cell is having a wire, and that wire is very thin, 20 micron, maybe of the order of your hair, or some even smaller, thinner than that. And then things were transferred down underground, and then it is being installed. You see, this is the magnet, the red one which I showed you in that picture, the magnet in the Alice setup, and then it is being transferred there, and it is placed. This is beam pipe, and this is installed here. So this is how the whole journey of building a detector. First you design it. First there should be some goal, which particle you want to measure. Accordingly you design it, fabricate it, test it, build it, integrate it, and then install it. Okay. And this is one picture where you can see people visiting PMD Lab in VCC. This is the installed PMD in the Alice. This is the entire setup underground, which I said bigger than Hawa Mahal and heavier than Eiffel Tower. This is the entire system. And our then President Pratibha Patil also visited CERN to see what we are doing. So now let us summarize. So for these kind of experiments, what are the components required? Okay. So detectors we need, because we need to detect the particles, because they are the only source of information. Electronics, because after the detection their signal we have to record the signal, for that we need electronics. Then readout and data acquisition, to collect the recorded signal we have to collect the signal, right? And then computing servers are required to store the collected data. Control and monitoring tools also, because everything is underground, right? And when particles are colliding, then lot of radiations, so then you cannot go inside. So from outside you have to control everything. Computing simulations are required, because everything needs some simulation, right? Even the small experiments nowadays, they need some, for heat simulation. Okay, there are softwares available where you can simulate the heat transfer and things like that, or water flow. There are a lot of simulation tools available. Simulations are basically computer programs. And then of course analysis algorithm and computing tools for analyzing the data. I will tell you the data, I will show you how big the data is. And what are the steps? These are the ingredients you need to perform this kind of experiments. So ingredients are design, fabrication and testing of the detectors. This is first you have to do. Then also you have to design the chip for the readout, for the electronics, for record the signal. And when you want to buy something or want something, then you go to the market you and buy it, right? For example, you want some resistors or transistors, you go to the market, you buy it. But this electronics is not available in the market because they are very, very specific. So you have to design and build it, right? And that's why big collaborations are required in these efforts. Because we, for example, Bose Institute, we don't have any engineer, I cannot design a chip, right? So we don't have any manpower. So we have to collaborate with other institutes like VCC, there is a special electronic section there, they can design these kind of chips. Then also the readout system also you have to design, the data acquisition system. Then you have to integrate the entire thing, assemble them. Then you have to install it into the experimental hall and you collect the data. Once you collected the data, then analysis of the data and publication. That is what these people are doing. These three sitting here. They are,
The last step.
the last step, because by the time they join the PhD, this part is already done. They have not even involved in data collection, right? Rathijit was there in the data collection because he visited CERN and participated in the data recording part, but they are at this stage. So at some point of time they also need to learn all these steps. I don't know how, but it is good to learn. Okay, so now coming to the third part. So it's basically, now we want to probe a system. As I said, the aim of the experiment was to probe a system. And here also I will tell the story of only one probe. There are several probes because collision happens, a system is formed which is very short lived and particles are produced. There are n number of detectors. We discussed one detector. Similarly, after you detected the particles, there are n number of techniques and methodology you can apply to get information from the using these particles about the system formed. So we will discuss about something called jets. Okay, and this you have to remember that this is just, let us consider this as a QGP system. This you have to remember that this system is produced in heavy ion collisions. They are very short lived, very dense and very hot. Okay. So now jets, what are jets? So you have seen these jets, this is water jet, right? These are all water jets. So jets are basically, jets means when a tap water is there you don't call it jet, right? But then this kind of water you call jet. So it's basically high speed and collimated. That is the one important feature of jets. So here also in high energy heavy ion collision, we call these are QCD jets. They are high energetic collimated spray of particles produced in heavy ion collisions. So after the heavy ion collision happens, lot of particles are produced, right? And in that group, let us say, there are one bunch of very high energetic particle passing through in a very limited space that is collimated. Then such kind of objects are called jets. And that is what we do. I personally and this Abhi, Praten, they are also doing analysis on jets. Okay. So let us see what we are basically looking for. Now you can think of this kind of situation. This is a water jet. Okay. So now what will happen if there are obstacles in their path? What will happen? For example, these water jets are obstructed by this water jet. They will be modified, right? They will be no more collimated like this. Their speed will be reduced. So the jets will be modified. That is very simple thing, right? And depending on this obstacle, if it is very dense, they will totally stop. They will know. If you put a hard some metal thing there, then all jets will be stopped there. They will not penetrate. Depending on this obstacle, this jet modification will be driven, right? So jets in presence of obstacle or medium. So now let us think of this picture. So in collision, what happens? A system of QGP is formed, right? And suppose jets are moving in that system, then depending upon the density of the system, the modification will be there. So now if we can quantify the modifications and relate it to the medium, then you can tell about the medium, right? Looking at the modification, you look at the jet modification and you can relate it to the properties of the medium. Okay. So this is in a simple way, rather complicated. So now you can think of, this is the situation, this is a QGP and you want to probe that QGP. For example, suppose you want to measure the temperature of water in a glass. So what you will do? You will take a thermometer, put the thermometer inside it and then you will measure the temperature. Well, good, very good. And now you want to, let us say, measure the temperature of this, for example. So what you can do? You cannot put a thermometer there, right? Because this is very short lived, right? Can we put some external source like this? For example, in X-ray, you pass the X-ray through the object and you get some image. Can you do that similar thing here? The lifetime of this object is 10 to the power minus 23 seconds. In that small time you cannot pass on any external probe. Okay, so that is not possible here. So those speculations are gone. So then what else we left with? So you can rely on these self-generated hard probes. Hard probes are basically, in this collision, there are objects which are created at the very beginning and they are very high energetic. Those objects are called hard probes and jets are one of those objects. So they are created because they are created inside the system and they pass through the system. So you don't need any external probe, because anyway you cannot use external probe, but you can make use of this probe which is internal and it is generated inside the collision, by this collision itself. So there are so many particles and inside those particles, among those there will be a jet also, and then this jet, while passing through the medium, they will get modified, and then looking at the details of the jet you can try to infer information about the medium. Okay. Medium, when I say medium, it is QGP. Okay. So there are basically hard probes are high momentum, high energetic particle you can say, and there are so many such probes, but our interest is on jets. Okay. So now let us just, this is the event display. Okay. So you have, this is the transverse view of the experimental system. Okay. This is the collision point, and after the collision you can see there are two jets, back to back jets. You see there are a lot of particles going in this and this direction, and this event you can see three jets clearly. This is the reconstruction of all the tracks after the collision. This is PP collision. So in PP collision less number of particles are produced, and you can see here there are two back to back jets. Okay. You can see some more pictures in different way. Here energy is plotted along the z axis, and this is the x and y axis of your detector plane. So you can see there are two jets. Okay. So here huge amount of energy is and at one place, right? So jet by definition large energy and collimated. So this kind of a structure you can see here. This is also PP you can see here, and both are having back to back and having same energy. Okay. So this is also PP. Now think of a situation like this. So this is two jets you can clearly see. In proton-proton collision you have less number of particles produced, okay, because only two protons are colliding. But nucleus, so let us say lead, how many, what is the mass number of lead? 208. So 208 nucleons are here, 208 nucleons are here, and they are colliding. So you can think of so many particles will be produced, and the situation is like that. This is only one event, and all these lines, they are tracks. So you can see how many tracks are there, and in these tracks there might be few jets sitting here, which you can see how difficult it is to, and in this was for gold and this is for lead. This is the situation. So the entire detector is filled with particles only. This is only one event, and all the tracks are representing one particles. So there so many particles are there, and this kind of object might be sitting here somewhere. So you have to find those objects. So it is not that easy. It is little bit difficult, but doable, because there are techniques. These objects will be very high energetic. So if you put a cutoff on the energy, then probably most of them will be gone, and then you will left with this kind of objects. So there are techniques also. You can find them. So for jets, QCD jets, little bit more detail. So what happens when these protons collide? Then what is there inside proton? Quarks. Then it is basically quark-quark interactions. So in these interactions, if this interaction is very hard, means with large momentum transfer, then these two outgoing partons, two body scattering you have read, right? These are the two incoming partons, and these are the two outgoing partons. So if they have very large energy, okay, then they will split into many more partons. And finally, because as I said, partons means quarks and gluons. Quarks and gluons cannot be free. So eventually they have to combine and form hadrons. So that is called hadronization. Okay. All quarks and gluons should combine and form hadrons, and that is called hadronization. So these hadrons are there, and these hadrons final state particles, they will pass through the detector. Okay. So you have to put your detector, you have to detect them, and then as I mentioned, you have to find some algorithm, because apart from these particles there are other particles also, right, in that event, which are less momentum, which have less momentum and not the part of jet. So you need some reconstruction technique or finding technique of jets. So those are there, and once you do that, you can calculate your whatever you want to study about the jet, and then you can perform some corrections for the detector effects. These things I am skipping because these are lot. Then systematic uncertainties are to be found out, and then you can do the theory comparison. Okay. So this is a situation when there is no medium. Let us say there is no medium is formed, there is no QGP, just two proton collided and jets are produced. But suppose our goal was to study the medium. So suppose there is a medium here. Now everything is happening inside the medium. Okay. So in this case, there will be some modification of the jets. Okay. And then let us look at this. So this is the proton-proton collision where there is no QGP or no medium is formed. Two jets are coming out from the collision system. Okay. This is in heavy ion. Two jets are coming out from the collision system, but they are also passing through the medium. So they will be modified. And in a very simple way, what can happen? This, I think you can understand this. You see what is plotted here? This is the PT of the jets, okay, and this is the number, let us say. So how many jets are produced with this PT? How many jets are produced with this PT? Okay. So this is, let us say this is in PP, red one is. Let us say red one is PP. Now in heavy ion what will happen? Because while passing through the medium, jets will lose energy. Okay. So this number of jets which were having PT, suppose this one, this, it is momentum, transverse momentum. Let us say energy, call it an energy. Okay. So energy of, let us say these numbers are, these are the total number of jets produced with energy here. Okay. Now they will lose their energy in the medium. This is in proton-proton. So what will happen? These will be shifted towards left, right. So this point will come here, because these jets lost some energy, and they will be in a, when you plot them, their energy is less, so they will show up here. Similarly, some jets will totally lost, because they will lose all their energy. So in that case, if they are lost, then their numbers will be removed from here. So this blue line will be shifted this side and downside, and effectively if you take the ratio, then what will happen? Suppose you take the ratio of this one blue to red, then what will happen? It will be less than 1, right? And if it is less than 1, then this indicates that there is a medium, okay. And if it is 1, then jets are not modified, that tells jets are not modified. If it is more than 1, then we don't know, there might be some other effects, right? But if it is 1, then jets are not modified, means there is no medium. If it is less than 1, then jet modification is there, and also depend how much less. If the medium is more dense, then it will be even further suppressed. This is one important observation, or this led to the discovery of quark-gluon plasma. So this is, if you understand then you understand the discovery. So the quark-gluon plasma was discovered, one of the main observable was this suppression. Okay, this is called suppression because in case of medium the production is suppressed. Okay, and this is called the famous jet nuclear modification factor. In high energy physics, if you ask anyone about the jet modification factor, they will know. This is called RA. Okay. So let me close here. So this is what we are doing basically. So now questions, if you have something.
Sir, how can we know that there were jets? If we know that ratio is less than 1, then we know that there was a medium. But how can we know that the jets are, how can we compare initial conditions that ratio is what?
1. So in proton, this cross section, in the reference is proton, you take proton, but because if you just compare heavy ion, then from where you will get the reference, that is your question, right? So then we take two systems, you take proton as a reference and then heavy ion as a final thing. So then you compare these two. Okay. Our question? Any other questions?
We already know about the medium, right? Because we are doing the experiments, if we know whether there is a vacuum or whatever medium.
No, we don't know exactly. Because in heavy ion experiment also every time medium is not produced. Because this collision happens, I said, I don't know whether I showed that plot or not. I think that was missed. How many collisions happen per second? I showed that. It was not there or what? You see 600 million collisions per second, right? So every time medium will be formed, that is not sure. So depending, suppose two nucleus are colliding, then sometime they can collide head on, sometime there are partial collisions, sometime very partial collision. So depending on those, every time not necessarily medium will be produced.
So medium is basically when it collides and
the sufficient energy density is there, then the medium is formed. Okay.
not the outside.
Not the peripheral collision. In that case, medium will not be formed. Even for the PP, medium is very unlikely. But when nucleus really collide head on, then lot of energy is dumped, and then this melting happens and you get free quarks and gluons, that is medium. Okay, so do you want to conduct the quiz?
So
Maybe you should ask questions related to
this talk.
not the basic questions, because those were prepared for the school children.
Related to this talk. So what is QGP? QGP. What is QGP?
Quadrant Plasma.
Please look. I am asking definition of QGP. It's not full form of QGP.
Suppose two hadrons, like so many hadrons are there, and if we try to vanish, like if we
The wall.
so much dense, then we can see the medium where quarks live with just gluons and quarks. If we vanish the boundaries of hadrons, we try to by densing it.
Right.
That is all like.
Yeah, in some set that is true. So it's basically quarks and gluons moving freely over the hadronic volume. So it's within the range more than the hadronic volume. There is one important point also, that is called thermalization, because when you talk about a system, then its system has some properties, right? So then if they are all lying here and there, then that's not basically, then what kind of system that is. So you need some common feature about a system, and that is common temperature. So this system should be interacting enough such that they attain a common common temperature, not minimum, common temperature, and that's called thermalization. So it should be also in the thermal state, thermal equilibrium state. Okay, so he got one pen.
So
maybe in the end we will give them
maybe
everyone.
then
So
we'll give.
हाँ तो ठीक
So
है.
next question is how many experiments are going on the LHC ring?
Major experiments.
Major experiments.
Major experiments.
How many
Major
experiments are going on
at
that
LHC?
ring?
There are 4
4. Okay, good. And name them.
LSC or CBS?
CMS.
CMS.
LCB.
Alice.
Some
Hurry up.
Particularly
Rick is based in USA, right?
हाँ, Rick is in USA. So that was long back. Now it is running, but is most activity, because the energy is quite different, and higher the energy, you go more close to the Big Bang sort of.
Atlas is one of them.
Atlas, correct. And LHCb, the other one.
He
fourth
told
one.
LCB is and CMS, then Atlas, then what is left?
That's all Alice, no?
We are talking about Alice experiment and Alice so left.
No, in the beginning he told Alice.
Then he should.
Okay.
We'll keep the cap.
Then next question.
Full form of PMD. What is the full form of PMD?
Photon multiplicity detector.
Very good.
Okay.
Okay.
So which country built PMD?
India.
Okay.
There was another map in the Alice detector system where we saw Indian map, not only on PMD but there
On
was
the other
detector,
side,
sorry.
which detector it
The
was?
other detector,
Good. That was built by
I think you will.
India, and which institute?
SIA.
SINP, correct. Okay.
So
Okay, so I think we close the session. Okay, thank you for coming. Okay.